All right, now we're going to prove the case where n is equal to 3. So that is, we have 3 distinct monomorphisms from k to L. And we're going to suppose that we have these and that there is a dependence. Okay, so that n a1 lambda 1 plus a2 lambda 2 plus a3 lambda 3 is 0. This 0 on the right, this is the 0 function. It's not 0 the element, it's the 0 function. And that is, we're going to suppose we have a dependence where, of course, the lambda 1, lambda 2, lambda 3 are all distinct. Okay? We want to find a contradiction here. That is, well, we want to show that, one of the a's has to be 0. Well, if one of the a's is 0, then this reduces to the n equals 2 case. And we've already shown that we must have equality in the n equals 2 case. And so we're done in that situation. So we can assume then that none of the a's are 0. All right, cool. So none of the a's are 0. We have a combination of our lambdas that gives us 0. What does that mean? Well, as in the n equals 2 case, for all x, y, and k, a1 lambda 1 of, well, if we were to plug in just the x into each one of them, we would get what the 0 function does to x. The 0 function sends x to 0. And we can also substitute in a yx as well, and we also get 0 for the yx. Just as in the n equals 2 case, we're going to do something entirely analogous to that. And since the lambdas are not just linear maps, they're field monomorphisms, we can break the lambdas up under multiplication, of course. All right, cool. Now we are going to use that the lambdas are distinct. So since lambda 1, lambda 2, lambda 3, oops, I don't know why I did the ellipsis there. Lambda 1, lambda 2, lambda 3 are distinct. What does it mean to be distinct? Well, they're functions, so they're distinct as functions. That must mean that, well, there exists some y in k such that lambda 1 has a different output than lambda 3. And similarly, you could do the same thing with lambda 2, but in particular, lambda 1 and lambda 3 are distinct. So we know that there's an input that has a different output. All right, so let's call this one, I think, star. And maybe this one, we'll call this one, I don't know, box. We're going to multiply star by lambda 3 of y. All right, so when we do that, we're going to get a1 lambda 3 of y, lambda 1 of x, plus a2 lambda 3 of y, lambda 2 of x, plus a3 lambda 3 of y, lambda 3 of x is 0, still 0 on the right. Okay, and then what we're going to do is then we're going to subtract from, oh shoot, I want to call this other one box. We're going to subtract from this guy, that box down there. All right, so when we do that, what happens? Well, we have this common lambda 1 of x in the first two terms. So we're going to get an a1 lambda 1 of y minus a1 lambda 3 of y times lambda 1 of x. And then we're going to get an a2 lambda 2 of y minus lambda 3 of y, lambda 2 of x. And then the last terms, these guys are going to cancel because they're of course equal. So we have this this combination, and the coefficient of lambda 1 of x is non-zero. So we have a linear, and this of course this is true for all x in k. So we have a non-zero coefficient in the front because lambda 1 of y and lambda 3 of y are not the same. So this gives us a linear dependence among lambda 1 and lambda 2. But they're distinct. So again, by the n equals 2 case, that must we have a contradiction. So lambda linearly dependent, but by n equals 2 case, we cannot have a linear dependence among distinct monomorphisms. I'm going to write LD for linear dependence. Two distinct monomorphisms. And that completes the proof. So if you were to have three distinct monomorphisms, they are linearly dependent.